Dear students, today's topic number is EMWG-S1. The title of the topic is electromagnetic waveguides. So far we have studied the propagation of plane electromagnetic waves in an infinite unbounded region in vacuum and other media. We shall now study the propagation by means of guided waves, that is, waves that are guided along over a conducting or dielectric surface, such as two parallel conducting planes, rectangular and cylindrical hollow conducting tubes of any uniform cross section, which can support electromagnetic waves. Now, what is a waveguide? A waveguide is a hollow conducting tube, metallic. It could be non-conducting as well, but of uniform cross section, using for transmitting electromagnetic waves by successive reflection from the inner walls of the tube. Now let us take the first case of the waveguide, the electromagnetic wave propagation between two parallel conducting planes. Now let us consider the electromagnetic wave propagation between two parallel perfectly conducting planes of infinite extent in the y and z directions. The two planes are separated by a distance a along the x-axis as shown in the figure. Now here we have got, these are two conducting planes. This is the one plane which has the conductivity, infinite conductivity, and this is the second plane. They are two parallel conducting planes. They are separated by a distance a, 0 to a, x is equal to 0 and x is equal to a, and we will be bounding the electromagnetic waves traveling inside here, and they will be traveling along a guided path. We consider that along the y, here the plus y and minus y, they are open, unbounded. So we will consider the E field component to be constant, not varying. Only variation is taking place along the x. So we will set those boundary conditions as well. We will come to these waves, electromagnetic wave, and propagate inside this conducting plane has two configurations. One is a trans-electric and the other is trans-magnetic. We will explain later that, but at the moment we will just mentioning this thing. Since the planes have been assumed as perfectly conducting, any component of E parallel to the surface must be 0. So the parallel to surface means the tangential part here parallel to the surface, which means that electric field must always be perpendicular to the surface. So E field must be perpendicular to the surface, means here like this, we have shown here E is perpendicular to the surface. Here we will be having the E field perpendicular surface. We will considering the tangential component here, because it is a conductor. When it hits the conducting surface, that the tangential component we see is reflected back, so that component is equal to 0. Though we have perpendicular surface of the conductors, now the magnetic field being perpendicular to the electric field must be parallel to the surface. So H field will be parallel to the surface of the conducting plane. So here these are the boundary conditions, that the tangential component of E will be equal to 0, normal component of H will be equal to 0. So there will be normal component of E and tangential component of H will exist, where ET is the tangential component and HN is the normal component of E and H fields respectively. Hence the Maxwell equations subject to these boundary conditions at the surface of conductors and can determine the configuration of electromagnetic fields in the space for non-conducting region between the planes, that is air or vacuum. The Maxwell equations are of the form given as, this is the Maxwell equation of popular Ampere circular law. The curl of H is equal to the delta E by delta T. The other one is this is the popular Faraday law. Curl of E is equal to minus mu delta H by delta T. These two Maxwell equations we will be making use of that. So assuming that the E and H fields propagate as sinusoidal variations, so E is given as E naught E over j omega t, H is equal to H naught E over j omega t. Then we putting that into respective, that the differentials, taking the differential of E and H, then we have the following equations. Curl of H is equal to minus j omega epsilon E, and curl of E is equal to minus j omega mu H. Now electromagnetic wave equations for non-conducting media, we have now the del square of E is equal to minus omega square epsilon mu E, and del square H is equal to minus omega square mu epsilon H. So we took the refer to the previous topic we have done in electromagnetic wave equation for sinusoidal variation. We have done that before, so refer back to that topic. We have already done these calculations over there. So let us now express these equations. Express now these equations 3 and 4 in its x, y, and z components. Then we have from equation 3, which was the curl of H in x, y, this is the x component. We have got the delta hz by delta y minus delta hy by delta z equal minus j omega epsilon ex. You can do it through the determinant, the curl of H determinant method or matrix method as well. So we will see that these components at the are cancelled because of the boundary conditions. With respect to y, we don't see any variation, only with respect to x variation will exist, and with respect to z. So the other all variation with respect to y and with respect to all the other components will be equal to 0. Only variation we are taking, the propagation is taking place along the z, and the variation along the x. So delta by delta x components will survive, delta by delta z component will survive, only those differential operator will survive. So the we have these now component parts of H and E both. We have got these equations, equation 7, 8, 9, 10 and 11. So the cancellation of both terms are explained in the next page. We again further give this in this page. Similarly, from equation 5 and 6 we can express which is del square of E was equal to this. So we can express the del square by delta x square plus del square by delta y square of E, del square by delta z square of E is equal to this minus omega square epsilon mu E. And similarly for H, for del square of H, del square of H by delta x square plus del square of H by delta y square plus delta del square of H by delta z square is equal to minus omega square epsilon mu H. Now in equations in equations 7 and 12 in equation 7 and 12 from what we get those terms of E and H vanishes which extend along the Y. We consider the E component to be the constant. It is the not varying along Y. E and Z field are considered to be constant as being outside of the bounded region. Assuming that the wave is propagating in the positive Z direction as shown in the figure, and the variation of all field components in this direction may be expressed in the form e to minus gamma z, where gamma is equal to alpha plus j beta, is a complex wave propagation. When we include the time variation part as well, so we get the e to minus gamma z into e to j omega t. So all along total what we get e to j omega t minus gamma z represents the space-time propagation of electromagnetic wave in the z direction. Since the space along the y direction extends to infinite direction where no boundary conditions to be met, we can assume that the fields in the y direction are uniform. Already we have discussed that or mentioned that, but again we are mentioning it, and hence all the partial derivative with respect to the y vanishes in equation 7 to 12 as we have striked out those over there. Now let Ey, which we already said that this is a normal component, let Ey is equal to Ey naught e to power minus z gamma. In general, E is equal to E naught e to power, this is the minus gamma z, and H is equal to H naught e to power minus gamma z. So we just took the y part only here, so propagation is along the z, so we take the y component. Also we can also have the partial differential of Ey with respect to z, delta Ez by delta z. Ey by delta z is equal to minus gamma E naught e to minus gamma z, or simply equal to minus gamma Ey. Similarly, we can write the corresponding result for the z derivatives of the other field components. Making use of these results and fact that all derivatives of the y outside the boundary region are 0, we have the equations equation that is from equation 7, 12 and 13, 14. You go back and see those. The following conclusions are the results. The gamma hy is equal to minus is equal to j omega epsilon ex, equation number 16. Now refer to this is obtained from the equation number 7. Gamma ey is minus j omega mu hx from equation number 8. This is equation number 17. Minus gamma hx is equal to minus delta h z by delta x is equal to j omega epsilon ey from equation 9. So if you just put back the values, corresponding values, and we get the these equations, equation number 18. Similarly, minus gamma ex minus delta ez by delta x is equal to minus j omega mu hy, equation 19, which is from equation number 10. And similarly, delta hy by delta x, hence we get now the is equal to j omega epsilon ez. This is equation number 20, which is obtained from equation number 11. Delta ey by delta x is equal to minus j omega mu hz, equation number 21, which is obtained from 12. And delta 2 square delta 2 e by delta x square plus delta gamma square into e is equal to minus omega square epsilon e. So that is obtained from the equation number 13 as equation number 22. And delta 2 h by delta x square plus gamma square h is equal to minus omega square epsilon mu h, which is equation number 23, number 14. Now the solving the equation 16 to 21, these are the 16 to 21. yeah, 16 up to 21. 1621. Let us solve for the hx first. We are looking for those components of the field vectors E and H. For hx, we have from equation 18 we have minus delta hx minus delta hz by delta x is equal to j omega ey. Rearranging the above equation and putting ey, the value of we get the ey is equal to minus j. From equation 17, ey is equal to minus j omega mu hx by gamma. So putting this equation in this above equation, what we get, delta hz by delta x is equal to gamma hx plus j omega epsilon into minus j omega mu hx by gamma, bracket close. And the next page we have page 8, last page, minus delta hz by delta x is equal to the same previous, this further simplified, hx by gamma square plus omega square epsilon mu, minus delta hz by delta x is equal to hx by gamma L square, where we have replaced this whole term as L square. This is a very important term. We will see that coming into as the phase. So L square, that will be making an important role or part. So hx, what we get from here, is equal to minus gamma by L square delta hz by delta x. So similarly we can get for the other terms, ex will be equal to minus gamma by L square delta ez by delta x, and hy, using the analogy, we can use this one. You can solve it by yourself. We gave you this as an assignment. You do it in the similar way which we did in the previous for hx component. So hy is equal to minus j omega epsilon by L square delta ez by delta x. Ey is equal to j omega mu L square delta hz by delta x, where L square is equal to gamma square plus omega square epsilon mu. So here the equation from equation 24 to 27 represent the plane wave equation in its component form while propagating along the positive z direction. So it can be seen from the above equation 24 to 27 that there must be a z component. This is very bottom line. What we observed that z component of E and H, otherwise all the components will be zero and there will be no fields in the space. So here what we see, if you notice that in hx we have delta hz by delta x, because the wave is propagating along z direction, so we must have the z component of the edge. Similarly, ex, we can see the ez is there, the partial differential of ez with respect to x. Similarly, hy we see here again delta ez again by delta x, changing with respect to x. Ey again delta hz by delta x. So these are the main components which we're looking for: hx, hy, ex and ey, which we found these components, but still we have to find out the ez and hz so that we can find actual solution for the ex and ey and hy, hx and hx and hy. So with this we reach to the end of this topic. You can download this complete file and you can review that and all these steps, do it by yourself at your spare time, and you will be able to go through and figure out these equations. Okay, we will meet inshallah again with a new topic. Till then, Allah Hafiz. Thank you.